Hey guys, Mrs. Brunk here. Thanks for joining me in Geometry A. Today's lesson, lesson 9-2, is entitled Conditions for Parallelograms. And you might be thinking, wait, wasn't that the last lesson? Didn't we just learn about parallelograms? And you are correct. That's good memory, since it was just yesterday. But instead of it being properties of parallelogram, which was yesterday's lesson, today's lesson is entitled Conditions for a Parallelogram. So that's a real significant difference. So today what we're going to be looking at is some properties that maybe a figure might have that would then prove that it has to be a parallelogram. Whereas yesterday's lesson, we were told, yeah, these things are parallelograms, and then these were all the properties we know that are true of parallelograms. But now we're going to be looking at figures that we don't know for sure are parallelograms, and we're looking for evidence enough to support a claim that they are parallelograms. And so we're going to be learning the conditions for a parallelogram theorem and the different ways that we can prove something is a parallelogram. So the first part of the theorem says this. If both pair of opposite sides of a quadrilateral are congruent, then it must be a parallelogram. And if you look back at yesterday's lesson, that's basically the converse of the first part of the theorem we looked at today. It said if something is a parallelogram, then its opposite sides are congruent, and this just is the converse of that. It says if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral must be a parallelogram. So in other words, if we know that these opposite sides are equal in measure, that's enough information to say that something is a parallelogram. Now what I want you to do is between each part of this theorem, we're going to write the word or, because in order to prove that something is a parallelogram, you don't have to show all four of these things. You only need to show one. If you can show that one of these things is true, then that's enough. Like that's sufficient evidence. So part 2 of the theorem says if both pairs of opposite angles are congruent, then it must be a parallelogram. So that too is the converse of a theorem we learned in the prior lesson. So this is saying, say you know this figure has opposite angles being congruent, then that means it must be a parallelogram. Now think about some figures that you know that have opposite sides equal. Well, the ones that come to my mind right away that are four-sided figures, a rectangle, right? And because the opposite sides in a rectangle have equal length, okay, that means it actually is a parallelogram. And we'll learn that as we kind of put this whole family tree of quadrilaterals together, that in fact it is, that a rectangle is a parallelogram. Now, if we have a parallelogram that has opposite angles congruent, like say a square. Now a square has angles that are in opposite position that are equal because actually all the angles are equal, right? They're all right angles. Same with a rectangle. If you think about what a rhombus looks like, you know, maybe you associate that with having all sides equal, which would mean that the opposite sides are equal, or maybe that the opposite angles are equal, if you can kind of imagine and picture in your mind what a rhombus looks like. So anyway, that is another way to tell if something is a parallelogram. Or you could also prove that something is a parallelogram if at least two pair of consecutive angles in the quadrilateral are supplementary, then the quadrilateral is a parallelogram. So if you can find at least two pair of consecutive angles, so it's not enough to just find one pair, but we'd have to find, like, say, this pair and show that these add up to 180 degrees, which is not enough to really say it's a parallelogram because you're going to find that that's true in a trapezoid, because a trapezoid has at least one pair of parallel sides. But if you have two pair of consecutive, so if these down here are also add up to 180 degrees, then that would be enough. Or, so this is the final way to tell, beyond the fact that you could also prove that figure is a parallelogram by showing that both pair of opposite sides are parallel. And that would be using the definition, though, rather than the theorem. But the final way is if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So if you have a scenario like this where you have your diagonals drawn in and you know that those diagonals end up being bisected by each other, and you could tell that by, let's say, these things were marked on it like this, then you'd be able to say, hey, that thing must be a parallelogram. So in these examples, what we're trying to do is we're searching for enough evidence to show that the figure must be a parallelogram. So looking at example A, in order for this to be a parallelogram, we know that this angle, actually we'd have to be able to find more than just that angle. We'd have to actually find the one on the other side of this 50 degrees. So these angles would have to add up to 180. So that missing angle would have to be 130. And then so would N have to be 130 degrees, because you'd have to have at least two pair of consecutive angles being supplementary. So if you wanted to make sure that this was a parallelogram, then you'd actually have to know that this opposite angle is the same as the one on the other side. So it would have to be 126 degrees. And also these angles here would have to be the angle that makes 180 degrees with 126, which is 54 degrees. So that would be 54, and E would have to be 54 degrees as well. Now, in order for this figure in C to be a parallelogram, you would have to know that both pair of opposite sides are equal. But what that would mean is that if they were, then this unknown side here would absolutely have to be the same as the one on the other side. So it would have to be 22. And then the other two sides would have to be equal to each other as well. And we'd have both pair of opposite sides congruent. And D. So D, we got this angle right here. We're trying to figure out what value would ensure that this could possibly be parallelogram, which would also mean that this one down here would have to be the same. Both of these angles would have to be the rest of 180 degrees when you take 118 away, and that's going to leave us with 59. Yeah, nope, that's wrong too. 152. That's not even right. It's not 100. I'm so sorry. Oh my goodness, that was terrible. Let's try that again. 180 minus 118 is 62. That's what I was trying to say. Not 162. 62 and 62 degrees. So example 2 asks us to show that each quadrilateral is a parallelogram. So for the given values of the variables. So they give us a couple values for the two variables, and by substituting them in, we're going to see if we meet one of the criteria that was listed as being enough to prove something's a parallelogram. So if I were to take and substitute wherever I see the x's, put 7 in, so this side would become, that's 7 plus 14, that's 21. On the other side would be 7 times 3, which is 21. Putting in 4 where there's y's would make this part BA would be 20 times 4, which is, or 5 times 4, which is 20, minus 4, which is 16. And it would make the side across from it 2 times 4, which is 8, plus 8 is 16. And you'd have opposite sides being congruent if those were the values of x and y. Let's go ahead and make B be a U-try question. So using the values of Z being 11 and W being 4.5, and given this drawing here that looks like it's a parallelogram, see if you can gather enough evidence to prove by using one of those parts of the program that in fact this figure is parallelogram. Please pause the video now. All right, so we were able to verify that, in fact, the opposite angles in this figure were the same measure using the values of z and w that were given. And so we can confirm that this thing is a parallelogram. So let's wrap it up with looking at a few more of these possible conditions that could be met to make sure something is a parallelogram. So first of all, in C, I have to identify the variables that are given as 2.4, and for A, and B is 9. So anywhere I see an A, I'm going to put 2.4 in. So let's see, 2.4 times 7 is 16.8. So this side over here is 16.8. Now on the other side, that side is labeled as 2 times A plus 12. So 2 times 2.4, add 12 to it, I get 16.8. So we have enough information to show that a pair of opposite sides is equal. So now they give us the value of B to be 9. So substituting it into angle Q, 9 times 10 is 90. 90 minus 16 is 74. And if I substitute that in the other angle, 9 times 9 plus 25, that's 106. Now those angles are supplementary. Now on its own, just knowing these two angles, one pair of supplementary angles that are next to each other would not be enough to prove that this is a parallelogram. However, because we've got a pair of opposite sides that are also equal to each other, and this is a theorem, a part of the theorem that actually is not listed, but is an actual part. You have to do a little more reasoning and logic to get to this. But because this pair of angles is supplementary and they're same side interiors, that actually means that these two lines right here are parallel. And if a pair of sides is both parallel and at the same time they're equal, then that means that the other pair of sides would also have to be parallel because they're the same distance in between these two parallel lines. So that would make the other two parallel and means this would have to be a parallelogram. Now, there's not part of that theorem that directly says that. So if we wanted to support this claim, we would have to just connect some of these theorems together a little bit, like the same side interiors theorem, the converse of that, to show that the one pair of sides is both parallel and at the same time equal in measure. And our final example. So now they have something to do with the diagonals here. So what I'm hoping we're going to find out is that the diagonals bisect each other, because that is a way then to prove that this figure is a parallelogram. So taking x being 6 and substituting that in anywhere I see x. So I see it here, I also see it around here. And substituting it into this first part, 6 times 2 is 12, plus 2 is 14. And then down here, 6 times 4 is 24, minus 10 is 14. So we've got one pair of these little segments that are equal, meaning that n is the midpoint of that segment, and now we just got to do the same thing on the other side, the other segment. So this time y, they say y is 3.5. 6 times 3.5 is 21, and then add 1, that makes 22. And then 8 times 3.5, times 3.5, which is what y is, and then subtracting 6 gives us 22, and so sure enough, that point n is the midpoint of both of these segments, so these segments bisect each other, and therefore this must be a parallelogram. So and that's because diagonals bisect each other. That's our reason That's our part of the theorem. Oops, diagonals bisect each other. And that's part of the conditions for a parallelogram theorem. In fact, it's this part right here. This very last one right here. Right there. Okay? And let's go back and do that same thing with some of these other ones, see if we can identify the part of the theorem that says that that must be true. So in A, we were able to show both pair of opposite sides equal. So again, there's this one right here, right there. Opposite sides congruent. In B, we were able to show that both opposite pair of angles were congruent. So that was this part of the theorem. In C, we had to kind of string some of those properties together, so that wasn't a direct connection to one of those parts of the theorem, but just kind of putting a couple things together. And again, there was some instances where we saw, like here, where we had a pair of consecutive angles that were supplementary. In fact, here in B, we could have not used the opposite angles being congruent, but we could have used the consecutive angles adding up to 180 here, right? So we could have used either part of the theorem on this one. So I guess the key thing is that you have to remember this is really the opposite theorem from the one we learned yesterday. That one yesterday we knew these things were parallelograms, and we said, okay, if they're parallelograms, then we know all these things must be true about them. Now we're looking at it from the opposite perspective. We know all these things are true about these figures, and we then now can state that these things must be parallelograms then. So that does it for today's lesson. Thanks for coming to class.